Everyone, welcome back. Let's begin by understanding an important concept. Are all finite elements the same? The answer is no. Different engineering problems require different types of finite elements. For slender members like bars, beams, and trusses, we use 1D elements. For plates, walls, and shells, 2D elements such as triangular and quadrilateral elements are commonly used. When analyzing complex solid components, 3D elements like tetrahedral and hexahedral elements are preferred. We also have shell elements for thin-walled structures, axisymmetric elements for rotationally symmetric components, special elements for springs and dampers, and higher-order elements whenever higher accuracy is required. The most important point to remember is that there is no universal element for every problem. The right element should always be selected based on the geometry, the physics involved, and the desired level of accuracy. Now, let's look at the mathematical idea behind FEM. Every engineering problem begins with governing differential equations that describe the physical behavior of the system. These equations are then converted into a variational formulation, making them suitable for numerical analysis. Next, the domain is discretized into finite elements, and shape functions are used to approximate the unknown values within each element. All the individual element equations are then assembled into one global system of equations. Finally, we solve the well-known FEM equation, Ku equals F. After solving it, engineers obtain important results such as displacements, stresses, strains, temperatures, and reactions. In simple words, FEM converts complex physical problems into equations that computers can solve efficiently. Today, engineers rarely perform large FEM calculations manually. Instead, they use powerful software such as ANSYS, ABAQUS, COMSOL multiphysics, SolidWorks simulation, and NASTRAN. Although these software packages have different interfaces, they all follow the same basic workflow. First, create or import the geometry. Then, assign material properties, generate the mesh, apply loads and boundary conditions, run the solver, finally, visualize and interpret the results. Always remember, software is only a tool. Good engineering knowledge and proper interpretation of the results are far more important than simply knowing how to operate the software. The finite element method is continuously evolving with modern technology. Today, FEM is being integrated with artificial intelligence, machine learning, cloud computing, high-performance computing, and digital twin technology. These technologies allow engineers to perform faster simulations, analyze larger models, and make smarter design decisions. FEM is also finding new applications in electric vehicles, biomedical engineering, renewable energy, smart infrastructure, and additive manufacturing. As technology advances, the role of FEM in engineering will continue to grow. Let's now look at a simple practical application. Consider a metal fin attached to a hot surface. Heat flows from the hot base toward the cooler surrounding air. In FEM, the fin is divided into several small elements. After defining the material properties and boundary conditions, the software calculates the temperature at each node. The results clearly show how the temperature decreases gradually from the hot end to the free end of the fin. This type of analysis is widely used in the design of heat sinks, engine cooling fins, and electronic cooling systems, helping engineers improve thermal performance before manufacturing. Let's quickly summarize what we've learned in this chapter. Finite element method is a powerful numerical technique for solving complex engineering problems. It works by dividing a large problem into many smaller finite elements. We explored different element types, understood the mathematical foundation of FEM, learned about commonly used software tools, looked at future developments, and finally saw a practical heat transfer example. These concepts form the foundation for everything we will study in the upcoming chapters. Thank you for watching. If you found this lecture helpful, please like the video, subscribe to the channel, and press the notification bell so you don't miss the next lecture in this FEM series.